Hello everyone. Today we will discuss using PGVector for RAG systems. In this lecture, we will cover Retrieval-Augmented Generation, RAG, Embeddings, and PGVector, and how they work together to build accurate AI systems. Let's start with Retrieval-Augmented Generation, or RAG. RAG is a technique that connects large language models with external data sources. Instead of relying only on what the model learned during training, the system retrieves relevant information at the time of the query. This retrieved knowledge is then added to the prompt, allowing the model to generate a grounded and accurate response. This approach improves factual accuracy, reduces hallucinations, and is widely used in enterprise AI systems. The overall flow is simple. A user submits a query, the system retrieves relevant knowledge, and the language model generates a grounded answer. Next, let's talk about embeddings. Embeddings are a way to convert text into numerical vectors. An embedding model takes a piece of text and transforms it into a fixed-length array of numbers, for example, a vector with 1,536 dimensions. These vectors represent the semantic meaning of the text. This means that texts with similar meanings will have vectors that are close to each other in vector space. Because of this property, embeddings enable meaning-based search instead of simple keyword matching. Now, let's move on to PGVector. PGVector is an extension for PostgreSQL that allows you to store and search vector embeddings directly in your database. With PGVector, you can add a vector column to your tables and perform similarity searches using standard SQL queries. This eliminates the need for a separate vector database and keeps your data in one place. It integrates seamlessly with existing PostgreSQL systems while adding powerful vector search capabilities. Next, we look at vector similarity search. In this process, a user query is first converted into an embedding. This query embedding is then compared against stored embeddings in the database. PGVector uses a distance operator, written as less than greater than, to measure similarity between vectors. The smaller the distance, the more similar the content. By ordering results based on this distance and limiting the output, we can retrieve the top K most relevant documents. For example, a query might retrieve the 5 most relevant document chunks by ordering embeddings based on their distance from the query vector and limiting the results to 5. Finally, let's look at the full PGVector RAG architecture. The process begins with a user query. The application converts this query into an embedding using an embedding model. This embedding is then used to perform a similarity search in the PGVector database. The database returns the most relevant document chunks. These chunks are added to the prompt as context. The language model then processes this enriched prompt and generates a grounded, accurate response. This entire pipeline runs quickly and keeps all vector data within the PostgreSQL database, making the system efficient and easy to manage. Thank you.